Welcome back to Physics 142 Online. For today's class, we're going to consider two different topics. First, the diffraction grating, and then secondly, the limits on resolution of two separate objects when the light that comes from those objects passes through a circular aperture. And so that's a phenomenon that relies on our understanding of diffraction of the light as it passes through that circular aperture. But first, the diffraction grating. For historical reasons, we call this the diffraction grating. We could just as easily call it an interference grating because the understanding of it is really based on what we find out from the two-slit experiment. So even for a simple two-slit experiment, if we have a white light source, that the two-slit experiment and the pattern that's produced on a screen will separate the colors of a white light source. And the reason for this is using the condition for constructive interference for a two-slit experiment. If we solve for the angle, you can see that it depends on the slit spacing d, but it also depends on the wavelength. So in principle, different wavelengths will appear on the screen at different angles. However, what happens in practice is, unless d is really small, the different wavelengths in the visible spectrum will have fringes that overlap and can't really easily be resolved. And so a diffraction grating overcomes this limitation in two ways. Firstly, a diffraction grating has really small values of d. And in the demonstrations that we do in class, you can see this. They're so close together that you can hardly tell that you have individual grooves or individual slits. If d is small, what that does then, for a particular wavelength, it means that the angle will be larger. And so two different wavelengths will be separated more for a small value of d than they would for a large value of d. So that's one thing. And then using not just two slits, but using a large number of slits, where that n might be hundreds or even thousands of slits, that causes the interference on the screen to have peaks, which is the locations where you have constructive interference. Those peaks have narrow width and much larger height. So the intensity of each fringe is much larger with a large number of slits than it would with a small number of slits. So here is both a graphical and then a photographic illustration of what happens. Alright, so the red intensity pattern shows what we get with two sources. We get a peak at the center, maximum intensity, goes down to a minimum, and then appears again as a maximum. And that's what we see in the top photograph. Two sources, a bright fringe at the center, surrounded by two dark fringes, and then more bright fringes. When you add a third source, what happens is the individual bright fringes get brighter. And then you can see right in the middle of the dark fringe, a very faint secondary maximum appears. But take a look on the graph, take a look on the intensity graph with three sources compared to two sources. Now look at the blue curve, all right? There is a small peak in between the two larger peaks, but notice the intensity of the main peak is much greater with three sources than with two. And then with four sources, it's even greater, and so on and so forth. So if n, the number of slits, gets really large, these peaks get very high. And you can also see, if you look at the zero in intensity on either side of the main peak, you can see that these peaks are getting narrower and narrower as well. And that's not something that the photograph captures quite so easily because we're only looking at 2, 3, and 4. But if we were to look at something with 100 sources, we would see that the widths of these bright fringes would get narrower and narrower, and that makes the peak positions of different wavelengths more well resolved from one another. So that's what a diffraction grating does. And let's use the equation for constructive interference from a two-slit experiment, which is also the same, it holds true for a diffraction grating as well, to calculate the following. Find the angular spread of the entire visible spectrum when a white light source is viewed in first order, that means m equals 1, using a diffraction grating with 10,000 lines per centimeter. This is comparable to what you have on the demonstration gratings that we use in class. Okay, so here's the picture. Once again, it's always a good idea to draw a picture in these problems. I'm only going to show 5 slits, but again, we have lots and lots of slits where the slit spacing, the spacing between 2 adjacent slits, is D. And now we have white light, and it's important in order to solve this problem to understand what the wavelength region of the visible spectrum is. And commonly we will use 400 to 700 nanometers, where 400 is at the violet edge, 700 is at the red edge, and those are the limitations on human light perception. So that's why we call it the visible spectrum. So what we want to do in this problem is find the angle at which the wavelength of 700 nanometers will have a bright fringe, and then find the angle where the violet light will have a bright fringe, and then subtract those two, because that will give us the angular spread of the visible spectrum. Now, the reason that we have to go to the m equals 1 first order is that at the center, of course, there still is a peak there, a bright light, but all of the wavelengths will all appear at theta equals 0, which would correspond to m equals 0 in our equation. So all of the different wavelengths in the white light source will all be at theta equals 0, so it'll just look like a white light source. In order to see the colors separated, we have to go at least to the first order spectrum. So m equals 1 is what we plug into the equation. But the question then is, how do we find D? Because notice this does not say that D is 10,000 centimeters. It says we have 10,000 slits or lines per centimeter. So we need to know D so we can put it into the diffraction grating equation. How do we do that? Well, what we have here is actually, if you think about it, the reciprocal of D. D is the distance per number of lines, right? The distance between 2 adjacent lines. Well, that's the reciprocal of the number of lines per unit length, right? So if we have 10,000 lines per centimeter, then 1 over 10,000 is 10 to the minus 4 centimeters. So this is saying between 2 adjacent slits, the distance is 10 to the minus 4 centimeters, which is 10 to the minus 6 meters. So that gives us D. Now, that allows us very easily to calculate theta red, inverse sine of lambda red over D, that's 44.4 degrees. Theta violet, of course, is less because violet has a lower wavelength, and that turns out to be, with m equals 1, 23.6 degrees. So the angular spread of the entire visible spectrum is the difference between those two, which is approximately 20.8 degrees. Diffraction gratings are used in many applications in physical science, often where we want to find out what the wavelengths are in a particular source. So it won't be like this problem. We'll actually know what D is already, and then measure locations on the screen where we see a particular color, and from measurements of the angle and the knowledge of D, we can work backwards and calculate the wavelength. So that's often what diffraction gratings are used for in practice. Okay, now let's move on and cover this concept of resolution. And diffraction, because it represents the bending of light when it passes through an opening of some kind, diffraction imposes an ultimate limit on our ability as human beings who have a circular aperture that lets the light into our eye. It imposes a limit on our ability to resolve two different sources, to be able to perceive them as two different sources. So that diffraction, the bending of the light as it passes through the pupil, tends to blur the light that comes from two images by producing overlapping circular diffraction patterns. So here is the diffraction pattern for light from a single source passing through a circular opening. And instead of having parallel fringes, you have circular fringes. You can see at the center there's a very bright region, and then that's surrounded by a circle where destructive interference happens, and then another maximum where constructive interference happens. So this is kind of like what you would get if you took a linear diffraction pattern and imagine rotating it around an axis, and it would produce these circular rings. So that's for a single source. Now imagine, by contrast, that you have two sources, and so two sources where the light from both sources comes through your pupil. You would see two of these patterns, But if the two sources are far enough apart, you would actually be able to resolve them as two distinct sources. So there's overlap in the patterns, but anyone who looks at this pattern would recognize that comes from two different sources. So we would say if you see this kind of image, then the sources are well resolved, and so they're easy to distinguish from one another. But imagine an intermediate case where the sources are closer together and maybe further away, which makes the angle that we see them at smaller. What could happen is they could overlap so much, those two diffraction patterns could overlap so much that it's really difficult to tell, do we really have one source or two sources? And this is kind of the limiting case where this is elongated enough that you can tell you're really not looking at circles. And so if you saw this pattern, we could infer from this that you have two sources that are just barely resolved. So what we want to do is work out a mathematical expression for when two sources are just barely resolved. And that will depend on the diameter of the opening, in this case the pupil of the eye. It will also depend on the wavelength of the light, and it will depend on the angular separation of the two sources at a particular distance. So let's show how this works. Alright, you might remember that the expression for the minima surrounding the central maximum for diffraction through a single slit was a sine theta equals m lambda. Well, when you have a circular geometry, that equation isn't quite right, and it turns out that if we use the diameter of the circular opening to be d, that d times the sine of theta 1, which would be the first angle where you see a minimum, so that would be the first dark ring, that's equal to 1.22 times the wavelength. So for a rectangular slit, this would just be 1 times the wavelength. But for the circular case, the geometry is a little more complicated. So when you solve the expression for destructive interference, it introduces this factor of 1.22. Alright, so that is the angle which would give us the location of that first dark ring measured from the center of the pattern. So if we solve for the angle sine theta 1, it's 1.22 lambda over d, and since we're usually looking at sources that are far away from the circular aperture of diameter d, we can use the small angle approximation here, which, if theta is in radians, sine of theta is approximately theta, and that just simplifies the math a little bit. So here's the situation. When two light sources produce two patterns, we say, and this is an assumption, this is an approximation, but it's a good one, we say that they can just barely be resolved if the central maximum of one pattern, which is the center of that bright disk, falls exactly at the location of the first minimum of the other pattern. And so this is the picture that I showed you a few minutes ago, where these two, the dark ring around the source on the left is at the location of the peak of the source on the right, or approximately so. And so when that happens, the angular separation is 1.22 lambda over d, and we say this defines the critical angle of resolution. And this equation is known as Rayleigh's criterion. So alpha is just another symbol for that angle, but we call it alpha c because it's the critical separation. And two sources that have an angular separation greater than or equal to this will be well resolved for a wavelength lambda and for the diameter d. And you can see that if d gets smaller, then the angular separation needed to resolve them gets bigger. So the smaller the hole, the harder it is to resolve these two different sources and be able to see them as distinct sources. So let's do an example problem. How far away can you resolve the headlights on a car? We'll make some assumptions about their geometry. They assume the headlights are 1.5 meters apart and your pupil has a diameter of 4 millimeters, and then because light from headlights is generally white light, we'll use a wavelength value that's at the middle of the visible spectrum to do the calculation. So those will be the assumptions that we make. And the sketch is critical here. So here's a sketch that shows two point sources of light. These are the two headlights, and they're separated by a distance x. And you can see this is not drawn to scale because right in the middle of the sketch is your pupil. All right, and then on the far right is the retina, which is where the diffraction pattern actually appears. And so this is not drawn to scale at all. And interestingly enough, since the critical angle is in the equation, we don't need to know the distance from the pupil to the retina. And I think it's about 2.5 centimeters for most human eyes, but all we really need to know is the angle. So look at this sketch. The angle alpha between two point sources is given in this sketch as just that angular separation. So when the light comes from each of those and goes through the opening, one of them will produce an intensity pattern up here on the top of the screen, on the top of the retina. The other one, for the light that goes straight through, will produce an intensity pattern here. And this sketch shows that those two peaks are well resolved because they appear pretty far apart from one another. So what we need to do is use the Rayleigh's criterion equation and find out whether the angle that separates those two sources is larger than or equal to the critical angle, 1.22 lambda over d. That would be how we would answer the question, can we resolve these sources at a particular distance? This problem is reversed. We assume we can resolve them, and we want to find what's the maximum value of L that will allow us to resolve them. So it's an easy calculation. The minimum separation is given by Rayleigh's criterion for lambda equals 550 nanometers and d of 4 millimeters. If you do the unit conversion, you get alpha is 1.68 times 10 to the minus 4 radians. Pretty small, right? Now, in this geometry, the tangent of alpha, there's a right triangle here, is x over the distance L, right? The opposite side over the adjacent side. And that, for the small angle approximation, we can regard that to also be alpha, because tan alpha and sine alpha and alpha are all approximately the same for small angles. So this equation from the geometry of the sketch allows us to solve for L. L is equal to A over alpha. So think about it, okay? If we use the minimum value for alpha, and that comes from the Rayleigh's criterion, then the minimum value for alpha will give us the maximum value for L. And that makes sense because the further away the car is, then the headlight distance doesn't change, but the angle will change. The further away the car is, that angle alpha gets smaller and smaller and smaller. So at some point it'll get far enough away that the angle alpha will be at the critical angle, and then we'll just barely be able to see them. For any further distance, we would just see one single blob. And this is probably familiar to you. If you don't remember this, next time you're out at night and you're driving on the highway, look at a car that's really far away. And when it's far away, you can really only see one headlight. But then when it comes closer and you come closer to it, eventually you start to be able to resolve these as two distinct images. So L max, this is easy calculation. We've already got alpha critical. X we know is 1.5 meters from our assumption about the headlights, and so the maximum distance is 8,940 meters, which is pretty far, right? And in fact, that's not really the limit in practice. If we actually do this experiment and you try to figure out how far away can a car be where you can resolve the headlights, it's actually somewhat smaller than this. I did an experiment once and estimated that it's right around 1,000 meters. The reason for that is because there are other effects that limit resolution besides just the diffraction of light as it goes through your pupil. One of those effects, probably the most important one, is atmospheric light scattering. Scattering of light and the diffraction of the light when it encounters the molecules in the air in between the sources and the pupil. And that causes diffraction patterns as well, and that washes out some of the ability to resolve them. But this equation actually turns out to be a pretty good one, let's say if we want to apply it to our ability to resolve light coming from a distant source in the heavens, and we use a telescope mirror as the relevant diameter in order to figure out the maximum distance at which we can resolve two distinct objects. And this kind of equation also applies to other sorts of electromagnetic radiation. So we can use the same kind of equation if we're looking at microwaves or radio waves, because they, just like light, are all electromagnetic forms of electromagnetic radiation. So we'll do another one of these in class. I hope this has been helpful, and I will see you soon.